So I'm going to talk about bonding, metallic bonding to be precise. So metallic bonding. Now in metallic bonding we have metal atoms, and metals tend to be solids. So to represent a metallic bond and to draw a metallic bond structure, we need to draw something that looks like a solid. However, we're not going to have these particles touching each other, because what this represents is the extent of the atom when it's lost its outside electrons. So if we think of sodium, I'll draw sodium here. So this is sodium, and sodium has 2 electrons in its inside shell. It has 8 electrons in its outside shell, its next shell, and then it has 1 electron in its very outside shell. So this is our sodium atom, but actually in metallic bonding, this outside atom, outside electron is donated to the rest of the structure. So you can see actually what we've got is a sodium atom that's a little bit smaller, or a sodium ion that's a little bit smaller. And so this is what this represents. This represents the sodium ion that's just a little bit smaller. And this space that we've got in there is taken up by those electrons that have come away. So electron. Now, 1, 2, 3, 4, 5, 6. We've got 6 positive metal ions, and we've got 6 electrons that have been donated to the structure. Okay, so these are metal ions because they don't have a localized electron anymore. That electron's been donated. And these are free electrons. Free electrons. They can move in this structure, but we call them, because they're not associated with any of the atoms, they are delocalized electrons, and they're free to move. So free electrons, they're delocalized electrons, and this whole structure here where we see all of these electrons in all of these gaps, we think of it as a sea, and we call it the electron sea, or even the sea of electrons. Okay, now the strength of the bonds between the positive ion and the electron are very, very high. Metals are solid. Metals usually have a very high boiling point. So this strength of this bond is very strong. They are electrostatic forces of attraction. So electrostatic forces of attraction. Okay, and it's electrostatic because the metal ion has a positive charge and the electron has a negative charge. So we say it's an electrostatic force of attraction between a positive metal ion and a negative electron. Okay, so that is the definition of metallic bonding. Okay, definition of metallic bonding. Which is great. So we know that metals have a high boiling point, high melting point and boiling point, and that's because of the strong electrostatic forces of attraction. Okay, so that's one thing we know about them. So that's one. The second thing that we know about metals is they're very good at conducting electricity. So they are good conductors of electricity. And that's because they have this free electron that can move. Okay, if we put a potential on our metal, then that electron will move and it will carry charge. So the reason it's a good conductor of electron, it's got free electrons which can move and carry charge. Okay, and three things that we know about our metal structure is it's a good conductor of heat. Okay, so it's a good conductor of heat. And why is that? That's because when we supply this with heat, okay, so if we put heat in here or in here at this point, then this metal atom will start to vibrate a little more. The electrons will start to vibrate a little more. The electrons will bash into the metal atoms and make the metal atoms vibrate a bit more. And the electrons can move and bash into another metal atom and make it vibrate a bit more. The electron can bash into another electron and make it vibrate a bit more and make it move and vibrate a bit more. And as it hits the metal atoms, it starts making the metal atoms move. And the vibration, so the energy from the movement that's been put in here from thermal heat into vibrational movement, the energy causes this temperature to rise, and the heat, thermal energy, will move down the solid. Okay, so we'll get conduction of heat. So we put heat in at this point and it will get conducted down as these start to vibrate more and make everything else vibrate more, and the electrons move and they hit other atoms. So that causes them to be good conductors. So they're a good conductor because the electrons can move and hit other electrons and metal ions, causing them to vibrate. Okay, and an increased vibration we see or we measure as heat. So as the vibrations increase, we see that and we measure that as heat. Okay, so that's all we need to know about metals and the properties of metals. However, we want to look at the strength of this bond. How can we increase the strength of that metal bond? Well, let's go back to our sodium atom. I'll just draw 6 of these. And you can see I'm drawing them in a regular arrangement as if it were a solid. And I'm going to put 6 electrons in the delocalized sea of electrons. So this, we could say this was our sodium metal. And let's compare it to magnesium metal. I'm going to use a different color. So this is magnesium metal. So magnesium metal, I'm just going to draw 6 magnesiums. Magnesium is in group 2. Magnesium will lose 2 electrons to become a metal ion. So this metal ion in our magnesium is a 2+ metal ion, a 2+ magnesium ion. And magnesium's lost 2 electrons. So each of those atoms has lost 2 electrons. So I've got 2, 4, 6, 8, 10, 12. I've got 12 electrons in this electron sea. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So here I've got a 1+ charge and I've got an electron, whereas here I've got a, do it in green, I've got a 2+ charge and I've got 2 electrons. So when we're looking at electrostatic forces of attraction, the bigger the charge, the greater the attraction. So if we're looking at this here, we've got an attraction, and we know that the melting point and the boiling point are going to be high because metals usually have a high melting and boiling point. But when we look at this, we can see we've got a bigger charge, a bigger positive charge, and we're attracting 2 negative electrons. So actually, the forces of attraction here are going to be much, much stronger. So the melting point is much higher than sodium, and the boiling point is much higher than sodium, simply because of that charge, simply because of the additional 2+ charge. Okay, so I've put in the melting and the boiling points for sodium and the melting and boiling points for magnesium, and we can see that melting point 97 compared to magnesium, which has got a melting point of 650, massively higher. The boiling point of sodium is at 883, which is what we would suspect because sodium is a metal, and it will be a very high boiling point. So this shows us the strength of that bond. So it is quite a strong bond. But when we compare it to the boiling point of magnesium, magnesium has a boiling point of 1091 degrees C. So it's a much, much stronger bond. So comparing the melting points, comparing the boiling points, we can see that an increased positive charge will mean that the electrostatic forces are much stronger. Okay, so I hope that's covered most of this in that particular way. There's only a couple more things that I need to talk about, and that is how metals tend to be ductile, which means you can draw them into a wire. So draw into, oh, wrong pen, let me get rid. So we can draw into a wire. So we can make like copper wire with it. And then malleable. Okay, they're malleable, which means they can be pressed into shape. So we want to press them into shape, so that means they can be pressed into shape. And it's all to do with the way that the metal ions are lined up. So they're lined up in this regular arrangement here. And if we apply a force in this direction, bearing in mind we've got a sea of electrons here, so all that happens is that these, say the top layer, all that happens with the top layer is that it scoots along. So they're all going to move along one. Okay, and they'll move along one. So they've moved into the gap, and then they're going to move along, let me just, like this, 1, 2, 3, 4, 5, 1, 2, 4, 5, 1, 2, 3, 4, 5. So we can see we've got the electrons in here, electrons in there, and all that's happened is that they've scooted along. So they've scooted along and just displaced. Now the bonds haven't been broken. All that's happened is it's just the metal atoms, ions, have just moved along that sea of electrons. Okay, so this is how they can be drawn into shape or pressed. So the layers, or the atoms, the atoms layers can slide. Okay, and that really does get us to the end of this metal bonding topic.